This video is on vertical motion in one dimension with air resistance. Question 1, true or false? According to Newton's second law of motion, sigma F and A will always point in the same direction. That's true because we have sigma F on the left side and A on the right side. So the magnitude on the left side is equal to the magnitude on the right side, and the direction on the left side is equal to the direction on the right side. Part B. According to Newton's second law of motion, sigma F and V will always point in the same direction. Well, this is false because acceleration is what you're doing. Sorry. Velocity is what you're doing. Acceleration is a change of what you're doing. So sigma F and V do not point in the same direction. Part C, according to Newton's second law of motion, the velocity and acceleration of an object will always point in the same direction. That's also false by looking at this equation. Question 2, give an example of an object when its net force or acceleration and velocity point in opposite directions. So we got two examples here. Number 1, a car is moving to the right, but it's slowing down. So V is to the right, but sigma F is to the left. V is to the right and acceleration is to the left. Example 2, an object is thrown upwards. When it's thrown upwards, it's moving up, V is up, but the acceleration is down towards the center of the earth. V is up, but the force of gravity points down. So it's moving up, but it's slowing down. So the point of problem 1 and 2 is to prove to you that velocity and acceleration do not always point in the same direction. Question 3, what is the meaning of static equilibrium, dynamic equilibrium? Static equilibrium is when sigma F is 0, A is 0, V is 0. Dynamic equilibrium is when sigma F is 0, A is 0, V is constant. Question 4, define free fall. Draw a displacement versus time graph, a distance versus time graph, a velocity versus time graph, a speed versus time graph, and an acceleration versus time graph for an object dropped from rest in free fall. So the meaning of free fall is there's an object in the air. The only force on it is the force of gravity. There's no force of friction. So the object could be moving in any direction. Up, down, left, right, at an angle upwards, at an angle downwards. Many people think free fall means that you just drop it from rest. That's not true. You could throw an object up at an angle. And as long as there's only the force of gravity, no force of friction, it's in free fall. So this is what a displacement versus time graph looks like in free fall. You see the slope increases as time increases. That means the velocity increases. This is a velocity versus time graph. You just drop it from rest, so initial velocity is 0. Velocity is negative as it goes down, because you want to graph an object dropped from rest. This is what the acceleration versus time graph looks like. You see it's always 9.81 down. So I'm saying positive y is up, negative y is down. Distance versus time, remember distance is always positive. And speed versus time, remember speed is always positive. Question 5, an object is thrown upwards in the presence of air resistance. So we do have force of friction now. Draw a free body diagram of the object when it is moving upwards at its peak and moving downward. So there's some things we have to remember here, memorize. Speed is directly proportional to force of friction. So as speed increases, force of friction increases. And as the object moves upward, force of friction decreases since the speed of the object decreases. And as the object moves downwards, the force of friction increases since the speed of the object increases. So hopefully these images will make more sense. When we throw an object and it's moving upwards, we throw an object upwards, force of gravity and force of friction point down. So in this case, the magnitude of acceleration is greater than 9.81 meters per second. And as the object moves up, the force of gravity is constant. The force of friction decreases since the speed decreases. At the very top, velocity is 0. So the only force we have is a force of gravity. The Earth is still pulling it down. Many students mistakenly say the acceleration at the top is 0. It's not 0. The Earth is still pulling it down. There's no force of friction at the top since the object is not moving. When the object is moving downwards now, the magnitude of acceleration is less than 9.81 because we have 9.81 down and we have a force of friction up. As the object moves down, the force of gravity is constant and the force of friction increases since the speed increases. So this arrow for the force of friction gets greater and greater and greater as we move downwards. And this arrow for force of friction when it moves upward is going to be less and less and less. Question 6. Use a pencil and ruler. Define terminal velocity. What is the relationship between speed and the force of friction? Draw a distance versus time graph, a speed versus time graph, and an acceleration versus time graph of an object being dropped from rest from a very high height above the surface of the Earth with both the force of friction and the force of gravity acting on it. So terminal velocity is when sigma f is 0, a is 0, v is constant. So that means the force of friction up equals the force of gravity down as an object goes down. Speed is directly proportional to the force of friction. So as speed increases, the force of friction increases. So if we drop an object from rest from a high height, in the very beginning, force of friction is low because the speed is low. As the speed increases, the force of friction increases. And something to remember, not all falling objects will experience terminal velocity. Terminal velocity is when force of friction up equals force of gravity down. That doesn't always happen. So these red lines represent objects with air resistance. The black lines show objects in free fall. So this is a mistake. This should say the red line shows an object with air resistance. It's a big mistake. And then the black line shows an object falling with only the force of gravity. So this whole thing is wrong. So you could see when we drop an object from rest in free fall, this black line looks like y equals 1/2 gt squared from a Suvat equation. This red line tells us that when we drop an object from rest, as time increases, force of friction increases. So as force of friction increases, the acceleration decreases. And eventually we get the same velocity. That's why you see this line with the same slope on the displacement versus time graph. Remember, this is a mistake. When we drop an object from rest in free fall, as time increases, the velocity increases. V equals AT. That's this black line, V equals AT. This red line is when we have an object falling with air resistance, so force of gravity and force of friction. So you could see eventually the velocity becomes constant, and when velocity is constant, acceleration is 0. Here we have an acceleration versus time graph. We're taking the magnitude of the acceleration. The black line is when the object falls freely. When the object is falling freely, there's only the force of gravity. And you can see the force of gravity is 9.81. That's the magnitude. The red line tells us the acceleration with force of friction and force of gravity. So when the acceleration is 0, we have terminal velocity. Acceleration is 0, sigma f is 0, v is constant. So force of friction up equals force of gravity down. Question 7. A parachutist jumps off a plane from a great height. After reaching terminal speed, the parachutist opens his parachute. The parachutist obtains a terminal speed for a second time and finally hits the ground. Draw a speed versus time graph of the parachutist. So it's going to look like this. So in the beginning, he starts from rest. As time increases, speed increases. When the speed is constant, that means force of friction up equals force of gravity down. Then he opens the parachute, the velocity quickly decreases. Then he gets terminal velocity again. And then boom, he hits the ground. Question 8. A 13 kilogram object falls in the air. Calculate the magnitude of air resistance on the object when its acceleration is 4. So let's let positive y be upwards. So that means acceleration is minus 4. And force of friction is in the positive direction. Force of gravity is in the negative direction. So let's solve for force of friction and we get 75.5 newtons. The positive sign means that the force points upwards. Question 9. A 3 kilogram object falls from rest in the presence of air friction. F sub r. F sub r, r means resistance force. Determine its terminal speed if the resistance force is kV where k is equal to 7. So let's set positive y point up. It says terminal speed. So terminal speed is when acceleration is 0. So now we have 0 equals kv minus mg. Let's solve for v, for velocity, speed. We get about 4.20 meters per second. Now this question is if you are taking university physics. So the meaning of college physics is algebra-based physics. University physics is calculus-based physics. So if you're only taking college physics, you could skip this problem in 11. If you're taking university physics, then you should understand these two problems. If you're not sure if you're taking university physics or college physics, then ask your teacher if understanding this question is necessary. Question 10. Determine an equation for the speed and displacement of an object if it is dropped from rest in the presence of air friction, where resistive force is equal to kV. So let the positive y-axis point down in this case. So we get sigma f equals ma, a is dv over dt, and sigma f is mg minus kv. So on the second line, we just divided mass from between the first line and second line. This third line, you could see we multiplied both sides by dt and divided both sides by g minus kv over m. Then here we put the integral on both sides, and this is a definite integral. So we put numbers or values on the integral. Here we evaluated the integral. Here we plugged in what we were supposed to after evaluating the integral. Here we rearranged by just putting L and G on the other side. Here we took the exponential of both sides. And you could see on the left side, e to the ln goes away on the left side. And e to the ln of g just becomes g. So then rearranging, we put g on the other side to get this equation. And then we just solve for v of t. So we get a graph that looks like this. The red graph. And the terminal velocity we could see as e goes to infinity, e to the minus infinity is 0. So the terminal velocity is mg over k. So we have this equation for velocity as a function of time. We know velocity is dx dt. Let's multiply both sides by dt. And this becomes a definite integral. I'm going to separate the integral on the right hand side into two integrals. Then I'm going to integrate the left side and the right side. And then plug in the values. You could see that e to the 0 is equal to 1. That's why we get this. Okay. So we could see as t goes to infinity, we get a number that's finite because the displacement goes to infinity. That makes sense. Okay. Question 11. Determine an equation for the speed of an object if it is dropped from rest in the presence of air friction, force resistive equals kv squared. Let the positive y-axis point down. So sigma f equals ma equals mg up minus kv squared down. So acceleration is dv over dt. Here I rearranged, very similar to problem number 10. Then I took the integral of both sides and put numbers on the integral. Here, I factored out the k over m in this term. And then here, I made gm over k to look like gm over k to the 1/2 squared. So in the denominator, I have something that looks like a squared minus v squared. Then I use partial fractions. So in the denominator, it looks like a squared minus b squared, which is equal to a plus b times a minus b. So I used this fraction and I multiplied the left side and the right side by this times this. And I ended up getting this. So A equals B. And if A equals B, that means I get this. And since A equals B, B becomes A, and then A becomes this. So now my partial fraction looks like this. This is what I started with. This is what I have now. So you can see it becomes two integrals, yeah? So this, which is what I had previously, now becomes this. And now, once again, we have two integrals. I just factored out the numerator. I factored this out. And then I took the integral, and I get this. And ln of a minus ln of b becomes ln of a over b. That's why I get this. And then I just rearranged to get this and took the exponential of both sides. Continuing to simplify. I was able to get v on one side. Finally, this is my equation for velocity as a function of time. Now that equation, velocity is equal to dx over dt. So now I could rearrange to make this equation look like this. Integrate both sides. Now I have these two fractions here. It's going to get a bit ugly, but take a look at what happened here. And finally, this is the solution for the displacement as a function of time. And as time goes to infinity, this should also go to infinity.